All right, in the last video, we saw that if we have some state, we can expand it in terms of an orthonormal basis, where our basis vectors are phi n and the coefficients are a n. And last time we found that if we wanted to find what these values are, all we had to do was come in with a bra of phi n on both sides and essentially compute the overlap between each basis vector and our state, or project our state onto each of our basis vectors. So another way that you'll see that this shows up is being written with something called a projector. So we could write V as being operated on by a projector with some basis. So this is what's called our projector. And what it does is, this bracket right here evaluates the overlap between the basis vector and our state V. And this then multiplies that coefficient times our basis states. So remember, there's an implicit summation here, so we end up with an an phi n. It's just that the an is on the other side. But this is often how we will write projections of a state into our particular basis. A really valuable thing about projectors is that these are what's called resolutions of the identity, or these things are equivalent to our identity matrix. So we can always multiply freely by these projectors. All right, so just to prove that, let's take both of these sides and whack them on our basis vector phi n. If we do this, if we have an orthonormal basis, or here it's just a requirement that it's normalized, but if we do this, phi n and phi n, that'll just turn into 1. Identity times phi n returns our state unchanged, and we get phi n equals phi n. So it is true that this projector is a resolution of the identity. So that's all good and well. But why would we use this? When is it useful to us? Well, oftentimes we have a state that's described in terms of x, in terms of position variables, right? If we have a square well, if we have a harmonic oscillator, we might use the Hermite polynomials to describe the wave function in some region. But we run into issues when we want to describe a free particle in quantum mechanics, because we end up needing an infinite number of our basis states. And so the trick that's often used dealing with free particles is we take our system and we view it through the lens of momentum, or we expand it in terms of our momentum eigenstates. So you've seen this in a previous video. And so what we're going to do is we're going to take our state V. I'm actually going to rename this to be F. And we are going to expand it in terms of our momentum eigenstates. We're going to project our system onto our momentum eigenstates. So in order to do that, in order for us to get somewhere with this, we're going to need a form for these eigenstates. And so, as you've seen previously, if you work through the definition of the momentum operator, you could find that phi p is equal to some normalization coefficient, we'll call this Cp, times e to the I px. So it is indeed a function of x. We have an x in here, but it also depends on the momentum p. All right, so we're going to evaluate this and see what pops out. But in order to do this, we need to know what our normalization constant is to get some fully specified answer at the end. So we often use shorthand when we're dealing with these. I'm just going, instead of writing out phi p of x every time, I'm just going to refer to this by a bra or a ket with a p inside. And so if we want to find this Cp value, we're going to take the overlap of two different momentum eigenstates. So if we do this, we get an integral from minus infinity to infinity dx. We have two different phi p's. We have one with p primes, one with regular p's. So this will be Cp prime. I'll pull out the other coefficient, Cp. Those get multiplied together. Then we have these exponentials, and the one with the p prime is complex conjugated. So that's e to the minus I p prime x, e to the I px dx. And if we simplify this just a little bit, then this will be equal to Cp prime. That should have been complex conjugated. Cp, pulling those out of the integral, minus infinity to infinity dx. And then we can combine these in e to the I p minus p prime of x. And so this might look familiar to you, but if it doesn't, I will let you know that we could take our old friend, the Dirac delta, and use its definition to simplify this further. So we need a little bit of information about these states. We need to know that they are, in fact, should be orthonormal. So if we take this overlap, we should get 0 if we're dealing with two different values of p. But if the values of p are equal, we should expect to get a 1 out. So in other words, we could write down a Dirac delta of p minus p prime. So this function is 0 everywhere unless p is equal to p prime. And using the integral definition of what this is, I could write that it's 1 over 2 pi integral minus infinity to infinity e to the I p minus p prime of x dx. Does this look familiar? If we look up here at our overlap of the two different momentum eigenstates, we see that this exponential looks almost identical. In fact, the only difference here is this 1 over 2 pi. We have Cp prime star Cp. So if we use this definition, if we plug this in for this entire integral, we would get that p prime p is equal to, in order to sub this in, we would need to multiply it by 2 pi. So we'd get Cp prime star Cp times 2 pi Kronecker delta. Not Kronecker, Dirac delta. So what this says is we get 0 if p prime and p are not equal. So we can get rid of this, setting p and p prime equal, and eventually, long story short, we can solve for this normalization coefficient as 1 over root 2 pi. Okay, so if we do this, if we use this definition, we find the normalization constants, we can then finally get to our Fourier transform, which is an operator that can just generally take us from our position eigenstates and express us in terms of our momentum eigenstates, right? That was the whole point. We wanted to take f, project it in the momentum basis, and then find out what we're dealing with. So I'll write down the Fourier transform equations down here, and we'll talk about what it is that we're seeing. 1 over root 2 pi, integral minus infinity to infinity, e to the minus I px, f of x dx. So this is our Fourier transform. If we take a function f of x, that's what we started with, and we want to project it into momentum space, we have to evaluate the overlap of the complex conjugate of our momentum eigenstate with our function f of x, our state f. And if we do that using this definition we found, we get our Fourier transform. It's also very useful to us to be able to go back in the reverse direction, and so I can write down the inverse Fourier transform. So here, what's happening, put a big old box around all this. What's happening here in our first integral is we have our function expressed in terms of x. We have this e to the minus IPX, but then we're taking a definite integral over our x variable. So if we find the antiderivative, we plug in x everywhere it shows up in our equation. So we're left with a function that no longer contains any x's, and it just is describing our system in terms of momentums, momenta. Then we could do the reverse process. If our function is described in terms of momenta, then we multiply times our e to the IPX and integrate over our p variable, making all of the p's that show up in our equation disappear, and the only dynamic variable we have left is that x. So our Fourier transform and inverse Fourier transform, you can see these show up in a few different ways. The only differences really are these factors of 2 pi out front. This is what's called the symmetrized version of the Fourier transform. This, if you apply this transform to a function, it is unitary. But sometimes there's other derivations where we have a 1 in front of here and a 1 over 2 pi for the inverse Fourier transform.